So we start off with some nice simple questions about entropy. Which substance has the greatest molar entropy? Well, when you're comparing the entropy of similar type substances, the one that's the largest has got the bigger entropy. Now, largest might be the one with more atoms, more bonds, in this particular case, more electrons, because all of these are the noble gases. So which is the biggest noble gas? And the answer is radon right there. Which of the following pairs has the greater entropy listed first? All systems are at 25 degrees Celsius. So we're looking at all the different possibilities here. Thus, for example, between CO and CO2, those are of course similar molecules. The bigger one has more entropy, so that's going to be CO2. Then H2S gas, H2S aqueous. These are the same substance, but one in the gas phase and one in the aqueous phase. Gas phase, of course, always lots more entropy than solutions. So therefore H2S is the one with the greater entropy. So that looks pretty good, as we're looking for the one listed first, of course. H2 gas versus H2O gas, again similar substances. H2O more atoms than H2, so therefore H2O has the bigger entropy. Two metals, again similar substances. Lead way more electrons than lithium, so therefore it's got more entropy. And then finally a solid, or that solid in solution. Well, in solution obviously much more entropy than just the solid, so therefore the NaCl aqueous has the greater entropy. So the pair that has the member with the greater molar entropy listed first is the H2S gas versus H2S aqueous. So the first two questions, we were looking at entropy of substances. Now we're looking at entropy of reactions. So we're going to think about the entropy on the reactant side, the entropy on the product side, and decide which one's greater. So in this first one, we've got two particles in aqueous solution, reasonable entropy, and we got a solid, hardly any entropy at all. So therefore more entropy, less entropy, thus the entropy decreases. Going to this one here, we got two solids and two liquids. On the left hand side we got aqueous, but then we got a gas. Anytime you bring in a gas, you can say that the entropy is going to increase. Obviously there are exceptions to that, but it's not a bad rule of thumb. And now down here we got 2 plus 7 or 9 gases on the right hand side. On the left hand side, excuse me, I'm going backwards. Right hand side we got 4 gases and 6 liquids, so we're effectively going from 9 gases to 4 gases. Massive a decrease in entropy for that particular one. Predict the sign of delta S for each of the following processes. So first one, we got solid and a gas going to no gas. So gas to no gas, that's going to be a decrease in entropy. So that's a negative delta S. Here we've got one gas going to 2 gases. So increase in the number of gases, increase in the entropy, so that will be a positive delta S. And then here solid gas, so we're making a gas going from no gas on the left to 1 gas on the right. Again, increase in the entropy, positive value of delta S. This is a cute one, which is the best explanation for the observed negative sign of delta S for the reaction calcium solid going to calcium ions. Now what one would expect here is you're going from solid to 2 aqueous ions, so you would expect it to be a positive value of delta S. These are going to have more entropy than just the solid is. Okay, so that's kind of what we're looking at here. Solid calcium sulfate is a network covalent solid, separates into ions in solution. If that was the reason for what we're looking at, delta S would be positive, or delta S is negative. So this isn't the reason that it's negative, because this would imply it's positive. Same thing for this one. More ways of arranging calcium and sulfate in solution than there are in the solid. So therefore, if that were the case, delta S would be positive. Thus, it is not an explanation of why it is negative. Now this one here, negative sign, exactly what you expect. Dissolving solid in solution, no, total hooey. We expect the opposite. So looking at these ones here, calcium sulfate dissolves exothermically, which leads to a reduction in the entropy of the solution. There's a relationship between the delta H of the reaction and delta S of the surroundings, but there's no relationship between delta S of the reaction and delta H of the reaction. So that leaves us with this last, the first one. Okay, The ions interact so strongly with water molecules. So in other words, what it's saying here is that these ions are really bonding onto the water, significantly fewer ways for the water molecules to arrange in the solution. Now that significantly fewer ways in solution is telling you there's a decrease in entropy, a decrease in disorder. Okay. Now what's cute about this one is ordinarily when we look at this, we think of it in terms of just the solute, because you always think, well, the solutions, the solvent's just floating around doing its own thing, hardly affected by the solute. But what we're saying here is that when it dissolves into the ions, those ions are interacting so strongly with the solvent that it affects the entropy of the solvent. So that is the one that would lead to a decrease in entropy, because we're messing with the solvent. We're making the solvent more ordered by putting these ions in there. So question 6, which of the following is true? In some spontaneous processes, the entropy of the surroundings decreases. Well, absolutely. If spontaneous, you're just talking about delta G altogether. Okay, delta G is associated with delta H and with delta S of the reaction. Now the entropy of the surroundings is just associated with the delta H of the reaction, right? If you've got an endothermic delta H, well then it's going to reduce the delta S of the surroundings, because the reaction is taking heat energy from the surroundings, thus decreasing the temperature of the surroundings. And if we decrease the temperature of the surroundings, the entropy of the surroundings decreases. Okay, but just because delta H is positive doesn't mean that it's going to be a non-spontaneous reaction. You can have a negative delta G overall with a positive delta H, as long as delta S is positive enough. So in other words, if the good delta S overcomes the bad delta H. So thus, yes, you can have spontaneous reactions in which the entropy of the surroundings decreases. That's just saying there's same thing as saying you can have spontaneous reactions even if the reaction is endothermic. Okay, next one, spontaneous process, the entropy of the system always increases. No. It is the entropy of the universe always increases for a spontaneous process. The higher the pressure of a gas sample, the greater is its entropy. No, because the higher the pressure, that means that those particles are banging into each other far more than they otherwise would, and banging into the sides of the container, which means that therefore there's more gas particles in there, so therefore less disorder, less entropy. Free energy of perfect crystal at absolute 0 is 0. This is a tough one. The actual third law of thermodynamics, of course, says that it is the entropy, not the free energy, of a perfect crystal at absolute 0 is 0. I'm not even going to get into the philosophical construct of a free energy being 0 in a perfect crystal, but the third law states entropy, not free energy. And finally, as chemical reaction proceeds towards equilibrium, the free energy of the system increases. Now, the whole idea is you're trying to minimize the energy of the system. So therefore, the first one, spontaneous process, the entropy of the surroundings decreases, was the correct one. So everything before this, thinking about S and delta S, and then effectively the second law of thermodynamics in that last question, is all leading up to the most equation in the entire world. Delta G is delta H minus T delta S. Now let's have a look at how that fits into this equation here. Well, what we're plotting here is we're plotting delta H and delta S as a function of temperature. So temperature going along that way, energy going up here. Here's delta H, it's 30 kilojoules per mole. It's an endothermic reaction, okay? And it's a constant with temperature because that's the assumption that we make at A level, although you can look at the thermochemistry extension topics to see how that's not quite true. But anyway, here, delta H is a constant throughout. Now, delta S is also a constant throughout, but of course, in this equation, it's not just delta S, it's T delta S. So we're plotting T delta S here against delta S is a constant. So essentially, we're just plotting T as we're going up here, okay? So therefore, or T multiplied by a constant. So it's a nice straight line when we're plotting out the temperature on the x-axis and the energy, effectively the T delta S component, on the y-axis. Okay, so the non-horizontal line is T delta S. okay? And the horizontal line is delta H. So let's look at the various parts of this graph. Let's start over on the left-hand side, okay? All the way over here, the delta H is greater than the T delta S, okay? So delta H is bigger than T delta S. Well, if delta H is bigger than T delta S, then delta H minus T delta S is going to be a positive number. And of course, if delta G is positive, then it's a non-spontaneous reaction. So this reaction is non-spontaneous down here at these temperatures. Okay, let's flip to the other side of the chart and go up here. This is now where our line T delta S is bigger than delta H, or delta H is less than T delta S. Well, if delta H is less than T delta S, delta H minus a bigger number is going to be a negative number. And of course, if delta G is a negative value, it's a spontaneous reaction. So up here, these temperatures here, it's spontaneous. These temperatures down here, it's non-spontaneous. Now, the point, of course, at which it goes from non-spontaneous to spontaneous is going to be right there, where delta H equals T delta S. Okay, if delta H equals T delta S, then delta G is going to be 0. And if delta G is 0, there's nothing happening in either direction, so we are at equilibrium. I should, of course, say there's the same thing happening in both directions, the same rate, so it looks like nothing is happening. So let's see what we got. Delta G equals 0 at 300 Kelvin, absolutely, because that's where delta H equals T delta S, so that's right. The reaction is spontaneous at 250. Well, here's 250. We said this was the non-spontaneous region, so that one's wrong. So that's why it's not now in red. And then the reaction is at equilibrium at 300. Yes, because that's where delta G equals 0. So the answers for this particular question, statements 1 and 3, are true statements. Now we've got several questions that are on the same general theme associated with delta G equals delta H minus T delta S. So an exothermic reaction has a positive value for delta S, which of the following is true about delta G? Well, if exothermic, right, that means that delta H is less than 0, or it's good. Positive value for delta S, so delta S greater than 0, again, nice. So we got nice and a nice, okay? The heat is going down, so that's nice, and the entropy is going up. Well, if the two components of delta G are both nice, a nice and a nice make a very nice. So delta G is always going to be spontaneous for an exothermic reaction with a positive value of delta S. The exothermic reaction 2NO2 gas reversibly goes to N2O4 gas is spontaneous, dot, dot, dot. Well, let's see what we've got. Exothermic again is nice. Delta H less than 0 is nice. Delta S here, though, we're going from 2 gas molecules to 1 gas molecule. 2 gases to 1 gas. We're losing some entropy. So delta S is going to be negative, which is nasty. So we have a nice, we have a nasty. Let's think about the all-important equation here. Delta G equals delta H minus T delta S. Well, you've got nice here and nasty there, which means that delta G is going to be nice when delta H is bigger than this. So in other words, at low temperatures, but when the temperature gets bigger, the T delta S, which is the nasty part, gets bigger. And so at high temperatures, delta G will be nasty. So delta G nice at low temperatures, spontaneous, when the nice delta H term is winning out.